let's look at wells. So wells are made by people to tap the groundwater. So it's an artificial discharge or taking water out of the subsurface. And then we'll talk about springs in a bit more later, but springs are natural outlets for groundwater. And really what happens is that the water table intersects the ground surface. So somehow that water table is going to intersect the ground and cause that groundwater to seep out of the ground and flow onto the surface. And so there's a couple of types of wells here. Here I have a picture of an ordinary well. An ordinary well would just be a hole dug into the subsurface that penetrates the water table. This would be the water table here. So we penetrate that water table, and then if you were to look down this well, you would see the water. You could see the surface of the groundwater at depth. And so you'd send a bucket down here and with a rope, and you'd scoop up some water, and you bring that up, and that would be your well water. Although most wells today are these pumps where we have an engine, electric motor, that will pump water out of the subsurface. And usually when that happens, we get this thing called a cone of depression, where the groundwater drops, and it's really a circular cone that'll go around it. Another type of well is one called an artesian well, and you'll see that in the lab that we do for groundwater. San Jose in the early 1900s had a number of artesian wells on the east side of San Jose. And so the key thing about these artesian wells, they penetrate a confined aquifer. So remember, the confined aquifer is going to be under pressure, and water will rise above the ground surface because of the hydraulic head. So in San Jose, what we had up in the Diablo Range, you know, the peaks to the east of San Jose, there's recharge that's going up here, right? So there's rain, and that water flows down. It's a natural recharge area, and then the deeper aquifers are confined, so they're under pressure. So if you were to make a well into that confined aquifer, the water would want to rise up to the surface called this potentiometric surface. So I've drawn it in red here. And you'd get a naturally flowing artesian well onto the ground surface. Now the analogy your book makes, I kind of like here, and I've sort of redrawn it, is we have some municipal water, a water tank up here. And they put it at a higher elevation. So usually with new neighborhoods, you'll see the water tank up on the hill. It's going to be higher than the elevations of the home. And so the hydraulic gradient or hydraulic head here will cause water to flow into the homes here, right, under a natural pressure, and that water will want to rise up to that potentiometric surface. Obviously, in your house, you have taps, so you turn the taps off, but when you want the water on, you turn the tap on, and water spills out into your sink or bathtub, right? And then you close it, right, otherwise the water will keep running. If you were to drill a pipe into this system here, that water would rise to the level of that potentiometric surface. So that's just that hydraulic head surface. And that's the concept behind these artesian wells. Now let's say a few words about springs, and we'll look at some images here in a moment, but they form under a variety of conditions. So it's where the ground surface intersects the water table, right? There's natural discharge. I mentioned that already. Groundwater flow collides with a steep impermeable barrier. So like if there's a fault, so a fault may make some fault breccia or fault gouge, which is an impermeable barrier, an aquitard, and it'll cause the water table to move up and eventually intersect the ground surface. We could have those perched water tables, but remember they're just temporary. Percolation runs into an impermeable layer and flows horizontally. So in horizontal strata, there could be an impermeable layer where the water can't penetrate, and instead of going down, it goes laterally and eventually comes out on a hillside or cliff face. Maybe there's a network of interconnecting fractures that channel groundwater to the surface, or maybe the ground surface intersects some of these natural fractures or joints in rocks. So for springs, again, here's an example of the water table intersecting the ground surface. So you get natural discharge that occurs here. Here we're seeing a structural spring, which would be here where we have a fault which develops fault gouge. And so the groundwater flowing downhill here will run into this impermeable layer and cause the water table to move up, resulting in springs. In fact, much of the San Andreas Fault can be mapped by springs. Then when we look at the perch water table, we've already mentioned this one before. And then here's an example where there's an impermeable layer here that's horizontal, and the percolation cannot penetrate this, so moves horizontally and produces these springs along a cliff face. So this is common to the Grand Canyon. Here are fractures, right? So these joint fractures that intersect the ground surface. Now, there's a section on hot springs and geysers in your text. And I know there's a quiz question describing, well, if your spring water flow slowed down and you wanted to continue it, one of the easiest ways to do this is to pump additional groundwater along these blue lines here that can recharge your system. So, and kind of the whole idea with hot springs is that the cold water seeps down, gets heated up, and the thermal energy drives this water to the surface at the springs. In some cases, you could even get these geysers. And we could also use these for geothermal energy. In fact, what we do, we pump cold water deep into the earth. It gets superheated and it turns into steam, and we use that pressure of steam to drive turbines, and the turbines will make electricity. A hot spring in Iceland, and obviously this is fed by the magma under the Icelandic volcanoes. Actually, I think this is Yellowstone, Yellowstone National Park, and we see these colorful blue colors and orange and red colors, and these are really strange bacteria or archaea that live in these pools. One place that hot springs, one rock type that typically forms is travertine, and you can see the layers of travertine that are forming in here. Remember, travertine is a type of limestone. It's a calcium carbonate. Geysers is boiling water and steam erupt cyclically from geysers, so it is a cycle. Groundwater is heated by shallow magma, but the weight of the overlying water prevents it from boiling. So remember, pressure inhibits boiling. When the pressure drops, bubbles form, the water transforms to vapor, and the water all boils at once, and this drives that geyser, right? The cycle repeats after the empty chamber is filled. So again, it has to do with water pressure and hydraulic head. What are some of the problems with groundwater? One of the main problems, excessive withdrawal or discharge, where we're extracting groundwater more quickly than it's being recharged. And one of the problems is that the land begins to subside and collapse, and it's a real problem, because once the land subsides, it ruins the aquifer. And remember, groundwater, 2/3 or more than 2/3 freshwater use comes from the ground. Now let's look at some of the problems with groundwater. And for starters, groundwater can be thought of as being renewable only on long periods of time, like 10,000 years. But the key thing is it's not renewable, or we say it's non-renewable in a human lifetime. So because groundwater provides up to 95% of the freshwater use that humans use, it's really important to preserve it and maintain its quality. Now, some of the problems that deplete the groundwater is obviously if we have withdrawal or discharge through pumping faster than the groundwater can be recharged, then we lower that water table, which will cause ponds and rivers to dry up. We could reverse the flow direction of groundwater through excessive withdrawal, again through pumping and also looking at that cone of depression. Coastlines where there's agriculture, too much withdrawal of fresh water will cause saltwater intrusion and contaminate the aquifer. And then one of the major problems is this pore collapse and subsidence. So we'll talk about each of these in order. Here's an example where before the city was built, we had a very high water table, a running rivers, swamps. After the city is built, the water table gets pumped really low, the river goes dry, the swamp goes dry. Excessive pumping will cause a cone of depression, which will create a reverse flow direction of the groundwater. So in this first image, we see groundwater flowing in this direction. If there's any septic tank waste, you see it's moving away from the well. But if you start pumping the groundwater too excessively and you create a deeper cone of depression, you can cause a hydraulic gradient to occur here, and then suddenly you're contaminating your own well here. I talked about saltwater intrusion or saline intrusion. So near coastal areas, if you pump groundwater out faster than it's being recharged, then you can contaminate your local source of groundwater. Well, one of the ways to remedy this, and I think there's a question on the quiz about this, is you can actually reverse pump fresh water back into this coastal aquifer. Another problem is if we redirect groundwater in canals, we can cause areas to go dry. So here, this has actually happened in southern Florida, where you know, in the 1700s, when we first arrived here, we see that this whole area, the Big Cypress Swamp, was very wet. But as we redirected water in canals to coastal cities, you can see large areas have gone dry in the Everglades. And then again, the major problem is this problem with subsidence and the collapse of pore spaces. So the key thing is when there's water in the subsurface, the water acts as a hydraulic pressure that keeps or forces the pore spaces open. But when you withdraw that water and you don't allow it to recharge that following year, then what happens is these grains shift closer together because of compression, because of the overburden lithostatic pressure. The grains shift together, and the aquifer collapses. It reduces the porosity, and really you can't claim that. And one of the problems we see is we see land subsidence, and we see these cracks or fissures that develop along the boundaries of the basin. And this is one of the problems we see here in the Santa Clara Basin. And the lab for this week will deal with subsidence in the San Jose area. And when you look at this map, I want you to look at the green lines, which are the lines of equal subsidence. Basically, they're like contour lines. For example, in Santa Clara, we're seeing about 8 feet in here. Well, this is our map showing how much subsidence has occurred in the Santa Clara Valley. Also, there's a hydrograph that goes along with this. And when you read this, this is the height of the water table, right? So here you can see that the land surface early in the 1900s, the height of the water table was actually above ground. So we had springs, probably artesian wells, right? And then you can see as we started pumping groundwater, because remember the Santa Clara Valley was for a long time orchards before it became the Silicon Valley. And you can see the depletion that has occurred over time. This unusual positive recharge is, well, remember in the late 30s and 40s here, we had World War II, so we weren't pumping as much water, so there was a chance for recharge to occur. In fact, today, the regions of over here in Los Gatos, there's Vasona Creek and the Vasona ponds, and those are really percolation ponds. And and also there's some percolation ponds down here off of 101 just before you get to Morgan Hill. And these ponds are designed to try to recharge that collapsed aquifer. I mean, we won't really regenerate the porosity that it once had, but at least we're trying to maintain it and preventing any more subsidence. Because one of the main problems we see, you can see if we get any more subsidence over here by the bay. In fact, Agnew. In fact, there's a town up here called Alviso, and it's so close to the bay. Any more subsidence, the bay water is just going to inundate it. So that's one of the future problems with more subsidence in the Santa Clara Valley.